So I'm Xuejie Xiao. I'm from Neuros. So today we're going to share how we can build an Ethereum alternative Ethereum solution that continue to evolve in the coming years. So first, I work for Neuros Network Foundation. We are a big believer on layer solutions. We believe that layer one is most suitable for value preservation, where you can really do that transaction processing in layer two. And Neuros CKB is our solution for the layer one blockchain. It's actually a new permissionless proof of work secure blockchain. We have introduced a really new concept called CKB. I'm going to introduce that in the next slide, but here we believe it first fulfills a store of value concept. And second, it can align all the interests between storage and value and all the different parts in the blockchains. And thirdly, it can also enable better economics. And we also designed a new model called the cell model, evolved from the UTXO model, to make sure that our Neuros CKB can be the most flexible blockchain. And we also use RISC-V as the virtual machine layers for blockchain to make sure that our blockchain can have the maximum flexibility. And while we believe Neuros CKB has many novelties, today I'm going to only cover about this cell model and RISC-V part. So we actually start from UTXO, and we designed a new model called the cell model. If you look back into the UTXO part, it actually only has amount and lock. Amount says how many tokens you have in the current UTXO, and locks is actually the ownership part, where you ensure that this UTXO stays yours and no one can steal it. We actually expand this model into 4 parts: capacity, data, lock, and type. First, capacity has 2 meanings. Capacity on the one hand, capacity means how many tokens you have in your current cell, which is our new version of the UTXO. On the other hand, capacity also means that how many bytes you can store in the current UTXO. So on one hand, it can access a token. On the other hand, it also ensures that you only can store this much amount of data in your cell. And we actually introduced a new part called data. This is the part you can store your user-defined data in your cell. So one example is that you can store your smart contract in the cell in the data part. The other example is that you can store all the necessary information you need in the current cell. So for example, for ERC20 example, you can just store the amount of values for ERC20 token in the data part. This part is completely defined by you. We just assume it's a series of bytes. And we actually expand the lock part in the UTXO model into 2 smart contract parts. First part is lock. It continues to ensure the ownership of a cell. And the second part is the type. Type is a part that we introduced to ensure the cell transformation part. I'll explain what cell transformation we mean here in a bit. But first, in this slide, what I want to emphasize is that our definition of a capacity combines 2 words. First, it captures the value in the cell. The second part, it ensures you can only use this amount of storage space. And if you really think about it, in the blockchain, we only have transaction. And essentially, a transaction is just transform one set of cells into a different set of cells. You can say I have cell destruction, I have cell creation, but what really happens is that you destroy a bunch of cells, you create a different set of cells. We call this process cell transformation. And this means that in the blockchain, what really is there is just cell transformation. And the type concept we introduced here just capture this cell transformation. So in the type script, you can validate all the properties and all the features you have in the cell transformation phase. For example, in your ERC20 token, you can actually your type script can just ensure that the sum of all input tokens equals the sum of all output tokens, which means no one can forge new token unless it's guaranteed by the owner. And Besides Xiao model, the other part we introduced is the CKB VM. It's actually based, like most existing solutions, actually based on a real hardware CPU VM. It's based on the RISC file instruction set. RISC file has two novelties which are important in the blockchain case. The first one is RISC file is an open instruction set. There's no property, there's no loyalty fees, there's no proprietary part. Everything is open source. You can find RISC files complete spec online in BSD license. The second part is that RISC file is a frozen instruction set, which means it's frozen. It's designed for the hardware. There's nothing you can change. There won't be any hard forks needed to make sure to add or modify an existing instruction in the RISC file instruction set. So what we mean by introducing a CPU as a virtual machine is that we want to aim for the maximum flexibility, which means that when your virtual machine is really a CPU, it's actually the same as a CPU using our laptops. It can run all sorts of language. You can run C++, Rust, Go. You can run higher level language like JavaScript, Python, Ruby. You can actually even compile your Bitcoin virtual machine or EVM directly and run it on CKB. This means we have maximum amount of support. We don't want people to pick that. You should really use this because this one gets the most amount of use. We want people to use whatever they want. The first part enabled by CKB VM is actually you can ship your crypto algorithm as a smart contract. Currently in CKB, our signature validation contract is now written is now hard-coded in our blockchain. It's actually shipped as a smart contract. This means you can actually change your code to run a different signature verification algorithm. Our working example contains that we have implemented the same algorithm used by Bitcoin and Ethereum and run them directly on CKB. And in the future, if we want to use like when Schnorr algorithm or other signature verification become more mature, we can integrate that directly in CKB without needing any change from the official part. We believe that the combination of cell model and the unique VM in CKB can enable a lot of new use cases. One of the examples of those new use cases is the Ethereum. If we look at Ethereum today, it actually have several problems. The first one is congestion. Whenever a new popular DApp comes out, the network becomes really bloated, and the transaction fees just skyrocket. And we cannot, and many of your transactions will either need to reset them to a higher fee, or they'll just get completely ignored. The second problem is that Ethereum has this unlimited storage problem. If someone pays their gas, there's no limit on the storage they can use to in your block contract. Even if you are not using their contract, you have to pay for the storage of all the data their smart contract needs. There's nothing limiting everyone from bloating the space. The third part is EVM upgrading problem. If we look at EVM's EIP repo, there's like hundreds or even thousands of EIP still pending there. Many of them introduce new concepts to the VM, like Black2B precompiles or different things. But many of those things, due to many reasons, are stuck in the EIP forever. You don't see that. Every time when Ethereum gets an upgrade, you only see a handful of upgrades or a handful of EIPs that gets accepted and implemented in a VM. We want to change this problem. So the question here is that CKB has this max amount of flexibility, but can we prove that this we really have this amount of flexibility? So the idea is that can we build Ethereum directly on top of CKB? So today here, I'm going to introduce the Polyjuice project. This name actually comes from the Harry Potter series. It's actually an alternative Web3 implementation for Ethereum. Our goal here is not build a prototype project. We want to build a production project that's like at least 95% compatible with the existing Ethereum. So whatever tool you're using today, whatever Solidity contract you're using today, we want you to be able to use them directly on top of Polyjuice. The second part is that is actually use CKB directly as a storage layer or as a consensus layer. All your data is actually stored on CKB. You can just discard a Polyjuice, and the Polyjuice part is completely stateless. You can discard all the data you need and start a new Polyjuice state. You will reach the same amount of consensus there. And as I mentioned earlier, this works with our existing Ethereum solution. We have examples showing that Web3.js works here. We want to make sure all the current Ethereum solution works here. If someone doesn't work, it will be a bug. And this is how Polyjuice works. It's actually a separate server running besides CKB. When you are making a Web3 compatible query API query request to Polyjuice, it will translate this query directly into queries into CKB. You will then assemble the data return from the CKB and return to you in an Ethereum compatible platform. And when you send an Ethereum transaction to Polyjuice, it will translate this Ethereum transaction directly into a CKB transaction and pass that CKB transaction into CKB to make sure it's submitted for the consensus layer. What I want to point out here is that if you look at Ethereum transactions, it's actually in account model. But if you look at CKB, we derive CKB's cell model from the UTXO model. These are completely different models. The question here is how we can bridge those things. We'll explain that in a bit, but first I want to point out one thing is that this Polyjuice project has one novelty, I think, is that it brings a real working state rent model for Ethereum. So if you want to submit a new contract to Polyjuice, you need to make sure you're paying the storage you're storing the new contract. If someone's using your contract and if their action incurs more storage for your contract, this user needs to pay the cost. And what this means is that every single bit of cost on the Polyjuice layer for Ethereum is actually paid by someone. You have to pay for the storage for you to use. And the question here is how we translate an account model to a UTXO model. What we have here is like we have designed a different set of cells. Each of these cells can function serves a different unique purpose. And with the combination of these different cells, you can implement an Ethereum account in CKB. First cell is the main cell. Each Ethereum account in CKB will have a main cell. So if your cell feels confusing to you, you can just think cell as a UTXO with more features. And first, what this main cell does is that it stores necessary information for this Ethereum account, such as the nonce part. And based on what account it actually is, whether it's an EOA or a contract account, either has more font cells or data cell. First of all, EOA or externally owned account will have font cells. What font cell means is that the account sent by someone else to you. So suppose Alice wants to send Bob 100 Ether. What Alice does is that she just creates a new font cell containing 100 Ether for Bob. When this transaction lands on CKB, Polyjuice will automatically recognize this and shows that Bob's account has 100 Ether incurred. And different from an external owned account, contract account, on the other hand, has data cell. What data cell means is that Ethereum has different storage. An Ethereum account may have different storage, and those storage are stored in the data cell. So we can split the storage across different parts of the cell or UTXO, so that you won't have a single point of failure. And on the other hand, what I mentioned earlier is that the flexibility of CKB is also ensured by the CKB VM. What CKB VM ensures here is that while the logs and type different part of it, these two parts of smart contract, we can validate a lot of all the properties in Ethereum right now. So for example, in your log contract, we can actually validate all the Ethereum signature validation part. We can also validate nonce. We also validate when you're saying, I'm sending 100 Ether to someone, you actually do send 100 Ether to someone, and all your other funds stays yours. And what types ensures, on the other hand, is this cell transformation part. First part, we want to ensure that when you say you have 16 data shells, you really do have 16 data cells. The second part is that we want to ensure that when we are transferring a fund, we'll do a slight optimization to make sure all the funds in the fund cells are transferred to the main cells. And the third part is like, as a potential future, we can actually compile EVM directly to run it inside CKB VM to validate your Ethereum contract actually does the thing that it says it's doing. So with CKB, what we are promoting here is that a blockchain should really have the generator and the validator part. It does not make sense to have all the computations on chain. Some computations are better off the chain, so you have this computation parts off chain, and on chain you're validating this computation is actually right. We believe this is the future in blockchain that can enable more use cases for us. And I want to mention one point that we didn't design a CKB to be able to run Ethereum. We designed CKB to have the maximum flexibility. Being able to run Ethereum on CKB is actually a happy accident for us. We're happy to discover this use case and develop this Polyjuice project, but this is not our main focus. Besides Ethereum, there are also many other interesting projects that can be achieved by CKB. And let's look at all the problems we listed earlier about Ethereum and look at how we solved them in CKB in this Polyjuice layer. First, congestion problem. Earlier when we say this Polyjuice is actually right now just a DApp, but there's nothing preventing you from evolve this Polyjuice layer into a layer 2 solution. So you can have this layer 2 solution, you process all the users' Ethereum transaction, and like once a while, like for every 100 transactions, you send the data back to CKB to make sure it validates this data and it puts them in the consensus layer. This way you can have much higher TPS in this Polyjuice layer. And also one additional part is like there's nothing preventing you from building a CKB on top of CKB solution. So you can have a layer 1 CKB and can also have a layer 2 CKB. Then you can build your Polyjuice DApp directly on top of the layer 2 CKB. So with this layer solution, we are seeing more potentials here. The second thing is that we're solving this limited storage problem by introducing a state rank model for Ethereum. Everyone, when they are using, no matter when they are creating the contract or when they're using the contract, they have to pay for the storage. And with CKB's unique economic model, we can ensure that if you just let some tokens in a cell that is unused, the value in the cells will eventually be devalued. This is ensured by CKB's economic model. The third part is that we want to build a layer that can have upgradability without hard forking EVM. So since this Polyjuice runs as a DApp or as a layer 2 solution, if you see something in the EIP that you like, so if you really need Blake to be in a pre-compile for Solidity to achieve a new use case, you can just upgrade your own EVM. And as long as all the instances for running your Polyjuice applications are upgraded with this Blake 2B solution, you can just use Blake 2B natively in your Solidity code from today. You don't have to wait for like 6 months or even years for to persuade Ethereum's official team to implement this Blake 2B behavior and wait for another hard fork for them to upgrade that one. If you see something you like, you can use that one. If you have something you need, you can integrate that right now. And besides those 3 problems solved, there's more benefits. First one is that we are preserving compatibility and legacy. We don't believe it's right to say that, well, Ethereum 2 is coming, everyone should just use eVasm. There are tons of investment in Solidity and tons of developers who use Solidity, and we want to ensure that their investments won't be in vain. The second part is like, this is actually a debatable part. I'm not sure. Before I'm on stage, I'm not sure if I should include here. With this Polyjuice solution, we can have upgradable Ethereum smart contracts. So if your ERC20 token smart contract has a bug, you can just upgrade that smart contract, and everything from that point will be able to run in a fixed and cracked version in CKB. some might say that this defies the purpose of saying that. Some of say that this is against the purpose in Ethereum that once the smart contract is there, it should be there forever. It should have fixed behavior that no one can change that one. But that's debatable solution. So this is an optional part. You might want to use it, but you don't have to use that one. The final part is that Ethereum solution is starting to show its ages. It's designed in like 4 to 5 years, but in an industry that's growing so fast, 4 years can mean a lot. Today we see many more consensus solutions and many more scalability solutions in blockchain, and Ethereum has this problem that's really hard to solve. With this Polyjuice solution, we can bring you a modernized Ethereum solution that's working today. And one thing we're seeing right now is that there's a trend to persuade people to really build separate blockchain instead of the apps. But we believe that with a properly and better designed layered one solutions, you can really focus on building your DApp. You don't have to worry about this overhead about building a consensus layer or security layer if you don't really need them. If your solution is better off with a blockchain, then that'll be better. But if you don't need a blockchain, we believe we should have a DApp solution for you that works and is also flexible. And if you're interested in this solution, we'll be here in Berlin this whole week, and we have a lot of events planned. So if you want, check out this page, and we'll be here. Thank you.